So Carles Mesado is a chemical engineer by Jaume I University of Castellón. He has a PhD in engineering and industrial production by the Technical University of Valencia, and he's nowadays working as a nuclear technology engineer in ENUSA. So Carles, you can go ahead with your presentation. I'll leave you to it.
Okay, thank you, Alex, for your presentation. And in this video, I'm going to show you or to explain a little bit about the current magnetic confinement fusion projects from now on MCF. We are going to see projects that are being built or projects that are currently in operation. If I move here, okay. So after this video, you for sure will know what ITER is about because it's the main topic here, as you can see. But first, I would like to summarize a little bit what we saw the other days, the 2 previous days. So for confinement plasma, we have 2 main kinds of confinement, magnetic, MCF, and inertial, ICF. We're going to talk about magnetic in this video presentation. For magnetic, we have 2 main kinds of reactors. That's the tokamak and the stellarator that Enrique talked yesterday about. Let's say the scientific community has more confidence or more experience in tokamaks, so that's we are going to focus here today. But any technology here for fusion, we are going to face a lot of challenges. Raquel told us yesterday about these challenges, but they are really important in scientific community. But to face these challenges and to overcome these challenges, of course, we need international cooperation. And that's where ITER project comes into the play. So what is ITER? If you don't already know, ITER is a project. It's a big international project to research on magnetic confinement fusion, or MCF, only magnetic in this case. It's composed by 7 partners, especially the European Union, but also India, Japan, China, Russia, South Korea, and of course the USA. The main goal is to demonstrate the technical viability on magnetic confinement. The main goal is not to produce electricity or energy for commercial purposes. It is only to develop the technical viability. The building started in southern France in 2010, near Cadarache, and it's supposed to start operation around 2025, we hope. However, this is the first step in a ladder towards the final fusion power plant. So the first step is ITER, then it will come a demo, and finally proto. This proto will be the first fusion power plant, and commercially, of course. So if we dive into the main goals for technology, we want to produce 10 times more heat that with this input. That means we want to produce 500 megawatts if we introduce 50 megawatts. We want to produce stable plasma. As we saw yesterday, I think Raquel explained us that it's kind of easy to obtain an instability. We don't want instabilities, but we know it may occur, so we must learn how to control them. We want to keep fusion also up to 8 minutes. That may be not a lot for you, but I must tell you that the biggest tokamak reactor in operation is JET, which is in the UK. It can hold fusion up to 1 or 2 minutes maximum. So it's quite a lot, 8 minutes. We also want to obtain self-sustained plasma. That means that initially in the first stage, we need to supply heat to the plasma. However, at certain level, the plasma should keep moving on by itself. So it is self-heated, let's say. And we also want to improve the breeding technology in tritium. So those are the main goals in the technology we want to develop. We already see this picture hundreds of times if you are into fusion, but I want to show you it again. These points represent the reactors that are in operation nowadays. As you can see, JET here is this one. It's the biggest tokamak in operation. And we want to do a jump and go into the ignition zone. The ignition zone is the blue area. And ITER will be here, around here, where the red arrow is pointing. So, of course, you can see that both axes are logarithmic. So you can imagine that this is a giant jump because both axes are logarithmic. That's where all these challenges come from, but we must overcome these challenges. So I want to talk about a little bit what's the story behind us that led us today here talk about ITER. So it all started in 1958, where the first tokamak concept was presented. It was presented in a conference, the second conference of Atoms for Peace. It was presented in a paper. This paper was presented by a Russian scientist called Vladimir Mukhovatov. And of course, he is working at ITER. He's the equivalent Messi for fusion. Of course, he must work at ITER. Afterwards, in 1985, the more important people on Earth at that time, Sir Gorbachev and Sir Reagan, they bring together an agreement. And of course, this agreement was built because of economical effort. This agreement was to develop fission for civil purposes. And this agreement was made because they didn't want to spend all the money alone. So they need to join forces, let's say. In 1998, we had the first final design, and final design is in italics because we have several final designs, as we will see. In 2004, ITER is approved with an estimated budget of 5,000 million euros. But of course, we have delays in 2013 because we want to introduce the technology, because in all these years, the technology advanced. There are new materials, new simulation codes, new projects, etc., that we want to introduce in our ITER project. So there are delays, and we need to increase the budget. We increased the budget in 2017 up to 13,000 million euros. We expect, or we want to obtain the first plasma in 2025. Here you can see a Gantt diagram for the main milestones in this project. We are around here. So mainly we are starting building the reactor. And we're going to see pictures of the real site, the real ITER project, the real reactor, or what we have right now at least. So as I told you, this project is being built in southern France, near Cadarache. Of course, there is good weather, good wine, good food. We zoom in, we have this area. In 2011, it looks like that. It was not really promising, just a hole in the ground, but it's something. Then in 2012, we have this, and these cubes are the earthquake-proof foundations. 2015, we have this nice picture from the sky. 2018, we have this. It's starting to build something. And you may ask yourself what it looks like today. So we are going to see it. This is how it looks like today. This is the main reactor building. And we are going inside the reactor building. So this is the main hall. And under these lids, it will have the reactor, the real reactor. If we remove these lids, we have this hole. That's where the cryostat will be. And for those of you who like to see the things by yourself, I know you can visit this facility by yourself. However, I understand the waiting list is quite long. So I invite you to go to their webpage or to scan the QR code. So it will take you to a virtual visit, and I really enjoy it. So I really recommend you. You can visit several buildings, several parts of the facility. And of course, you can move through the axis of time. Another important question you might ask yourself is, who is paying all of this? So of course, we are a European Union. It's paying most of the budget. This is an example for 2013 in million euros. The European Union was paying 80 million euros. And the rest of the partners, the other 6 partners, they were paying each one around 20 million euros. Yes, we pay the most, but of course, we also get the most of the benefits. It's not a coincidence that we get the reactor in France, and in Spain, in southern Spain, Granada will get an experimental facility or laboratory to advance in materials for fission. I hope we get that soon. That may be a lot, 80 million for you, if we compare that amount of what we have in our bank account, but I tell you, it's not a lot for these countries or for the European Union. We can compare these amounts with what the income for Messi, Barcelona football player, or the income for Cristiano Ronaldo football player. Both of them have an income of around 30 million per year. So that's not really a lot. So if they are watching this video, I invite them to support this project with their income. if they do that for several years, we will have this reactor real soon. I hope so. They are watching this. In this picture, you can see the vacuum vessel. This is not ITER because remember, ITER is being built. This is JET in the UK, which is the biggest tokamak in operation right now. And because we have two men, we have a reference, we have an idea of what's the real size of this vessel. In ITER, this vessel will be around 2 or 4 times bigger. So what about after ITER? As I told you, this is the first step in a chain of steps. The first one is ITER, then we'll have demo, and finally we'll have proto around 2050, and that will be the first commercial power plant by fusion. Before ending this presentation, I would like to talk a little bit about other projects. In this table, I summarize most of the tokamaks in operation. I would like to focus right now in JET, which is the biggest tokamak in operation. It has a power of 16 megawatts, and we want to jump in power up to 500 megawatts to ITER, and then demo 1000 megawatt. So you can see the jump is quite a lot. For accelerator, I have the same table. You can see there are less accelerator in operation. That's why we have more experience, or we are more confident in tokamaks, and that's why we choose a tokamak for ITER. I want to focus first on the first one, the German, which is the Weltenstein 7X. Sorry for my German, Kevin. And I also want to focus for DJ2, which is in Madrid, here in Madrid, Spain, which is a research accelerator in the CMAT. So here we have a picture for the Weltenstein 7X German accelerator. You can see it's really complicated, the shape. So it's easier to operate, as Enrique told us yesterday. However, it's difficult or more difficult to build. Here we have a person, so you can have a reference for the size. And that's why they say this is the dream for the scientists, but it's a nightmare for the engineers. So as a conclusion, or the main ideas, I would like to summarize what we are talking about here in the first video of this course today. So fusion could be a big share in the future energetic mix, along with renewable energies that we all know today. We still need a big development in technology, materials, project codes, etc. For that, for example, we are going to build this IFMIF Dones lab in the southern Spain soon. And for that, we need international cooperation. And in that sense, ITER project is moving forward in that direction, in the good direction, let's say. And the path to follow, as I told you, there are several steps: ITER, demo, and proto. Proto will be the first commercial power plant. It's supposed to be in operation around 2050. That is 30 years by now. However, scientists already say 30 years ago that we will have fusion energy in 30 years. That's why they say fusion is the energy of the future, and it will always be. Thank you for attending this course. This is the last slide. So I give the word again to Alex. Thank you.